So I think we can start today's session.
Ma'am, like consecutively, one more session was happening. Uh,
Okay.
one session is from 6 to
Eight, yeah.
8, and another consecutively start from 7 to on the
Yeah.
same day itself.
On the same dates, yeah.
Uh,
Actually, two people will be assisting you. So,
like, can this be a bit time gap? Like, since service taking from 6, can you start from 7:30 or so if it is convenient for you?
actually, the thing is, whoever wants to join, they can join in either of the sessions. This is a problem solving or a doubt clearing session. So, it's not compulsory that you have to join both.
Like, it will be useful if we
Yeah,
get
if you
both.
can, yeah, like I'll talk to them because there is an overlap between the two. So, I think that class is still going on, right?
No, sir, they winded up today earlier, but
Okay.
if it continues for longer time, then it will be a problem.
Problem. Okay. So that was from 6 to 7 today.
That was from 6 to 7. So
And it
if
was
you
taken
extend until
by, who was it taken?
7:30, it was taken by a PhD student from IIT Bombay.
Okay, fine, fine, fine. Okay. So either I'll talk with that particular person and so we can adjust the time among ourselves, or let me see if I can talk to the NPTL people and keep a time gap of at least 30 minutes between the two sessions. Then let me work this out with them.
Okay, ma'am. Thank you.
Yeah. So, and has anyone from this group attended that session?
Yeah, I did, and
Okay.
many of them did.
Okay, and
Right.
what was the pattern like?
Yes.
Yeah, was it a problem solving session or is it a doubt clearing session actually?
It was like he briefed the all first weeks. He briefed everything, and then he started problems.
Okay, okay. Yeah, so so now let us start our session. So you know the course, right? It is Fundamentals of Electronic Device Fabrication. And compared to a normal NPTEL course, I think the content here is usually like most of the content in this particular course will be subjective based. There are very less objective or say numerical related problems. Most of it will be concept related or subjective questions that you'll probably face in the examination. So in our sessions, what I'm planning to do is first we'll have a very brief summary since the other person is taking a summary. Like I'll take a very brief summary of what was taken in the particular week, and following that we will be having a number of questions we'll be solving each day. And after that, in case you people have any doubts from the previous week, you can ask them. And if, say, a group of students feel that some particular topic in the videos are not clear or should be taken again, and upon request, we can keep a session where we do a topic discussion kind of thing. That also can be done, but the thing is that you should tell me in advance. So I'll give you my mail ID, and you can also contact me to the mail ID whether you have any doubts or you want any like you want to clear any doubts on any specific topic and all those things. So anything related to the course, if anybody has any doubts, and people who are planning to like write the examination, please do enroll as soon as possible. I think it ends by the end of August or so. So whoever is planning to write the exam, please do enroll as soon as possible. Yeah. So these are the course details. The course is taken by Professor Parshuraman Swaminathan, who's a professor in the Department of Metallurgical and Materials Engineering at IIT Madras. And our course plan is such that first we will have an overview of what is semiconductor device fabrication, then followed by operations like oxidation, doping, and lithography. And in week 3, we will be looking at fabrication processes like etching and growth, process evaluation, and so and so. And finally, in week 4, we will see process yield, clean room design, IC logic, and packaging. So this particular tutorial session is organized every Tuesday from 7 to 9. As one particular person said, let me see if we can make any arrangements so that there is like less overlap or no overlap between the two sessions. Yeah. So speaking about me, I am Santara Krishnan. I'm a research scholar in soft matter and complex fluids lab at IIT Madras. So I'm a PMRF scholar, and as part of our PMRF tenure, we are supposed to interact with students for 1 hour every week. And so this is my mail ID, sandra.pmrf@gmail.com. Please do everyone please do note it down. So in case you have any doubts or you have any queries or anything, you can just mail me in this particular mail ID. So can everyone please take down just in case? Yeah. So session goals, as I said, is that usually whatever NPTEL courses you'll be taking up, you will be having like a number of videos that you have to see, and you'll watch the videos and you'll do your practice assignments and submit them and so and so. So to make this particular process a little bit more interactive and for a more what you call streamlined way of interaction between students, we have arranged these live tutorial sessions so that whatever doubts you have, whether it is related to the topics or whether it is related to the examination or anything related to the NPT, the course procedure in general, you can talk to us. And if you have any grievances like you need any particular help or anything, that too can be conveyed through us. So we will be discussing the practice assignments as well as in case you have any doubts with the submission assignments, we'll discuss the answers after the submission deadline is over, because before the submission deadline, I'm not supposed to give you the answer. So after that, I can help you with solving the practice assignments as well. Then, as I said, doubt clearing sessions can be conducted, and topic discussion, as I said, only if many people feel that a particular topic has to be discussed again, topic discussion sessions will be done. So what I'm thinking is that we will have this just a simple problem, like we will have a set of sample questions, and in each week we'll solve such questions. So today's session we will be keeping it short and just as an introductory session of what will be for the upcoming weeks. And fundamentals of electronic device fabrication is comparatively, I would say, a simple course. And if you go along with the videos, like as soon as the videos are released, if you can cover them in the same week itself, I think it would be easier for you since it is a subjective kind of subject. So for example, here we have a question which asks for the SI unit of electrical conductivity. So we know that resistivity is ohm meter, so ohm inverse, meter inverse will be one of the answers. The other one will be Siemens per meter. So usually for this particular course, we have such kind of questions. For example, the second question is in band diagrams, the highest occupied energy level is often called. Can anybody tell me the answer?
It's a valence band matrix.
Sorry?
Option C.
Yeah. So now I think we can go to today's problem solving session. So do you have any doubts related to the course or anything else like registration course, how the exam will be, etc., etc., etc.? If you have any doubts, you can ask right now. And I request all of you to join on time so that it will be easier for everyone. Yeah, you please go ahead. Yeah, somebody had raised their hand. Rely me, I guess. Does anybody have any doubts? Anybody? Or shall we move on to today's questions?
Yeah, ma'am, we can.
Yeah. Okay. So, everyone remembers the course contents for this week, right? So first, the course content was about the IC history. So let me just give a brief recap. So first, we saw about IC history. Everyone remembers what were diodes, how they evolved into triodes, and later on the solid state transistor, and so and so. Then what was the Moore's law? Can anybody tell me what is Moore's law? Anybody? So this was discussed in week one content. So what is Moore's law? Anybody? And it's not like I am evaluating you based on these questions or anything. You can go through your notes or you can use an electronic media to check the answer. So it's like a study experience. During this 1 or 2 hours of class, make use of it such that you learn a part of it so that you need not spend more time on it. So if anybody can check and tell me what's Moore's law.
Number of transistor per square inch of vapor doubles every 2 years.
Yeah. So that is the Moore's law. Then we saw what were wafer size and interconnects and so and so. Then the main content I would say was the overview of the IC fabrication process. So to fabricate an IC, initially we need a silicon wafer on which we do the oxidation layering, etc., etc., etc. So as a first part, how do we go from the SiO2 to an electronic grade silicon EGS? So this is what was mainly discussed in the first video, I guess. So that process, so it involves the submerged arc electrode process followed by converting it into EGS, and then converting it into a single crystal Si through two processes, Czochralski and float zone. And finally, this particular wafer will be sliced and they will be given flats. And these wafers will then be used for the IC fabrication. So, and after this, there will be processes like layering, patterning, doping, and finally heat treatment, and where we get our final IC. So in the upcoming classes, we will be seeing each of these processes in detail. For example, layering, doping, patterning, and heat treatment, and so on. So in the first set of videos, we'll only see the overview of the IC fabrication process, as well as how to convert the SiO2 into electronic grade silicon. So can anybody tell me the difference between metallurgical grade silicon and electronic grade silicon?
Like it is based on the amount of impurities.
Yeah,
EGS is normally purer.
yeah. So if you say like EGS is polycrystalline and it has impurities in the ppm level. So metallurgical grade, if you compare, the amount of impurities will be much higher. And for electronic equipments or IC devices, we need much purer silicon. That is why we go for this conversion process.
Ma'am, can you tell an impurity in a range? It is in the range of what?
It's like EGS we'll say in ppm level. Anything greater than that would go to the metallurgical grade silicon.
Okay, ma'am.
Yeah. So, and this EGS will be converted into the single crystal ingot and with a particular plane, like we know, like wafer slicing and grinding, right? P type with the plane of 111, it has a particular shape. N type with 100, it has a particular shape. Like that, we'll convert the single crystal and finally it will be used for the IC fabrication process. Yeah. So, this is the overview of what was taught in the first set of videos. So, now let us go to the practice questions. So, first question is the first electronic amplifier, that is, first electronic amplifier, that is a precursor to the modern day transistor is,
A triode.
sorry,
A triode.
yeah. So, for others, I'll repeat the question again. So, first electronic amplifier, which is a precursor to the modern day transistor, is a triode. So, can you tell me what is a triode?
It's a three-terminal device
Yeah.
which works on the principle of thermionic emission.
Yeah. So triode basically has three terminals, an anode, cathode, and a grid, and it is similar to in a modern day transistor, which has the source, drain, and the gate. So that is the first electronic amplifier, and it is a precursor to the modern day transistors. And whatever questions we are discussing here, I'll upload the PPT in the particular in the specific drive link. The video will be uploaded in YouTube, and the questions whatever we are discussing will be uploaded as a PPT in the drive. So it's not like you need to take notes. You can just listen and learn and think that's all. So second question is, what is the Siemens process? What is the Siemens process? So and also it would be better that all of you can try answering. So if anybody can unmute and let me know what is the Siemens process. Anybody? You can just give it a try. It need not be correct or anything. You can just give it a try. What is the Siemens process?
Hello,
Converting.
Yeah, hello. Somebody.
The MGS is converted to
MGS to EGS.
Yeah. So everyone answered correctly. Basically, Siemens process converts MGS to EGS. So EGS is much purer. That is used for the IC manufacturing, and it has impurities in the ppm level. So that is EGS. This is metallurgical grade silicon. This is electronic grade silicon. So Siemens process basically converts metallurgical grade silicon into electronic grade silicon. So in that case, so like if you see the whole process, how does this? First process is submerged, sorry, submerged arc electrode process. So what is the submerged arc electrode process? So now we will see the whole process one by one. What is submerged arc electrode process? Anybody?
Converting SiO2 to MgS.
Yeah. Basically, SiO2 or quartz is converted to MgS. So what happens during this process is that SiO2 will be mined or getting it as SiO, that is quartz we will be getting from quartzite, and then this SiO2 will be treated with carbon to get silicon carbide, which is then converted into our metallurgical grade Si, and it takes place at a very high temperature of about 1600 degrees Celsius and so on. So and here we have SiC again. SiC again gets treated with SiO2 to get SiO plus CO and Si. So this process is repeated in a submerged arc electrode process, and finally we will be getting the metallurgical grade silicon with which is about 98% pure and has mostly aluminium and Fe as impurities in them. So that is the submerged arc electrode process. Basically, SiO2 is our ore or quartzite. It will be treated with carbon to get the metallurgical grade silicon, which is about 98% pure. And now this NGS has to be converted into EGS. That is what is done in the Siemens process. Siemens process. So here what happens, whatever Si we got from the submerged arc electrode process gets treated with HCl and it becomes SiHCl3. And this SiHCl3 will be reacted in a fluidized bed reactor at 300 degrees Celsius or so, and fractional distillation will be carried out and finally reduced using hydrogen, and then we will get the electronic grade silicon, EGS or electronic grade silicon. So basically what happens, Si is reacted with HCl to get SiHCl3, and then in a fluidized bed reactor at about 300 degrees Celsius or so, it gets treated and HiHCl3 is then reduced using hydrogen so as to get the electronic grade silicon. So this is a repeated and loop process. So in each steps again there will be traces of HiHCl3 and this will again be reacted with Si, and finally at the end we will get the electronic grade silicon. And electronic grade silicon, as we already told, it has in ppm level impurities. So is the submerged arc electrode process and Siemens process clear? Yeah, if you see your summary, you can see a flow chart of what happens. SiM, like a metallurgical grade, it reacts with HCl, then hydrochlorination happens. So that reaction is given. So even if you can't memorize the whole thing, just a step-by-step overall picture of what happens during a Siemens process would help in the exams, I would get. So then what happens, this EGS, has to be converted into single crystal. And to convert them into single crystal, we use two processes. Can you tell me what are the two processes for converting them?
Jotrowski and Flotzon.
Yeah. One is Jotrowski and the another one is Flotzon. So, what is Jotrowski process? Simply if you can tell what happens during Jotrowski.
Ma'am,
Yeah, please go ahead.
Firstly, we introduced Jotrowski method.
Yeah.
And this is the dominant method, and majority we use this method, and 80 to 90% silicon wafer can be manufactured by the Jotrowski.
Okay.
And if you go for the lab and scientific research, then very precise silicon wafer is required. So we go much for the float zone. That is the very proper, pure, and here oxygen contamination is very less.
Very less, yeah. So basically both processes, what they do is that they convert the EGS into a single cylinder, and what happens is that in case of the Jotrowski process, what happens, from a molten bath of silicon, we will be using a rotating disc, and whatever a seed crystal will be kept, and upon pulling this from the molten bath, we will be getting a single crystal ingot. While in case of float zone process, there will be a localized heating, and the seed crystal will be kept, and along with this immediately in contact to the seed crystal, there will be a molten zone, and with progressive heating and cooling, we will be getting the single crystal ingot. So that is what happens in Jotrowski and float zone process. So is that clear? In one process, we will be using a molten bath, and from the molten bath, we will be making, and the other case, we will be using localized heating of the ingot, which creates a molten zone and then cools it. And based on the seed crystal, the single crystal ingot will be formed. So once the Chokralski and float zone process is completed, we will get the single crystal ingot, which is then sliced into thin wafers. So, and the next thing that becomes important there is like naming, or let's call it how to identify a crystal of wafer. For example, I'll ask a question now. Yeah. So a wafer basically has two flats 90 degrees to each other. What type of wafer is it?
P100.
Sorry?
P100.
Yeah, basically it's P100. So an explanation, I'll say, for example, if you have something like this, what is it? Yeah, there is no flats. It's just one side will be, there is a primary flat. This is known as the primary flat. The rest will be the same as it is. This is P111.
Ma'am, can I ask a question?
Yeah, sure.
Actually, ma'am, I joined the late this session.
Okay.
So I actually asked about this pattern. Actually, P11, P100, N11, and there is an angle, one primary and one secondary. What is the meaning? Actually, I understand this is the three-dimensional space.
Yeah.
And in three-dimensional space, there is many patterns. But here, sir, told only two types pattern. One or 100.
Okay.
And there is an angle. So then what is the 100 and angle? Exactly so.
Like basically what we are trying to say is that suppose you have a wafer like this. Suppose you will say, yeah, you have your single crystal ingot something like this. Suppose you have a cylindrical, say, single crystal ingot like this. This is somewhat round. This is how your single crystal is. And this particular ingot, all planes are such that it is oriented in 100 or something. Like most commonly in IC manufacturing, we will use either 100 or 111. You see, these two are the most efficient one. But these two planes are parallel to the surface are most efficient in case of IC manufacturing. And our entire single crystal ingot we have like that. So this ingot we will slice into very thin wafers. We'll just cut them. You will just cut them and finally you will get a wafer like this. And now you have to identify it. Once you have made the wafer, like you need to identify it, whether it was P111 or whether it is P100, etc. So to identify that, what we do during manufacture is first you have the round thing. You'll just cut this part off so that it becomes like this. Like this. So in the IC industry, it is understood that this is P111. Just imagine a very thin piece of like a sheet. You know filter paper, right? It looks somewhat like that. So if you have this, and this is known as the primary flat. If you just slice off one edge horizontally, that is known as the primary flat. If you have only one primary flat, it is known as P111. Just for identification purpose, we do that. Like once manufactured, we need to identify like which one we are using for our process, right? So that is why we do these kind of things. Suppose you have a primary flat like this. Suppose your wafer is, say, something like this. If your wafer looks like this, so for that one, what we will do is that this is the primary flat and this is the secondary one, 45-degree one. So that is the N type one.
No, ma'am.
Yeah. N type 1 and it is 111. So is that clear? So primary flat means this horizontal part and this is the secondary flat. If the primary flat is horizontal and the secondary one is at 45, then we will identify it is N type and it is 111. So is that clear?
Yes, ma'am, clear. And ma'am, one more thing.
Yeah.
Why we are cutting this primary and secondary? Why we are not cutting the proper circle shape?
No, like if you keep it like this, we have four types, right? We have P111, Then we have say P100, we have N111, then we have N100. So to identify the first one, the basic one, we will be keeping like this, that is our P11. So you are asking why we are not keeping it as it is.
Yes, ma'am, exactly.
That I don't know, maybe for identification purpose, initially it was like,
Certainly for identification.
yeah,
Then if you give a wafer, and how will you like you have to measure its resistivity so as to identify it is a N type or a P type,
yeah,
and orientation will be a very difficult to identify. If a manufacturer itself, if he marks and send, so
then it
immediately
will
we
be
can
easier
see
for
that and
others. Yeah,
identify it. Yeah, for that reason. So if he sends like everything round, he will be confused what it is.
what it
Oh,
is.
okay.
Yeah,
It means just for identification and our convenience,
yeah.
we are just naming
Yes,
this type of
yes,
Yeah,
nomenclature.
this
yes,
is like
yes.
a
Okay.
internationally accepted standard. Wherever you go,
Okay.
P11 will have this particular shape.
Okay. Yes. Got it, ma'am.
Yeah,
Thank you, sir.
yeah. And one
Thank
more
you, ma'am.
thing is, if you have seen these wafers in reality, they're very fragile. Like they are not as hard, and these will be very thin. So in the manufacturing process itself, it will be like instead of labeling, what they do is that they will give it a particular shape and it will be sent. That is what happens. Yeah. So is that clear?
Yeah.
Yeah. So, so in first videos, can anybody give an example of a heat treatment process that is done for these IC wafers?
Ma'am, layering, patterning, doping.
Yeah, in that we have final section is layering is there, patterning is there, doping is there, heat treatment is there, right? So layering means what we will be doing an oxide layer on top. Doping means we will be adding impurities. So what do you mean by this heat treatment of
Heat,
ice? Yeah,
heat treatment means I think if we go heat treating, then silicon wafer is silicide is formed,
yeah,
and that is the proper metaling purpose,
yeah.
metaling contact purpose.
Yeah, exactly. So basically, heat treatment process, what it includes is that silicide has to be formed after metal deposition. So, and each of these steps, as we mentioned, right, layering, doping, patterning, etc., 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 those will be explained in detail in the upcoming weeks. So, this is just an intro. I just wanted you people to keep this in mind. That's all. Yeah. So then, next question is portion of a wafer that is a standalone unit, that is it can work by itself. What is that particular portion called? Basically, in a wafer, you will have many regions, and each region will be scribed or marked into different sections. So, if a portion of a wafer that can work as a standalone unit, that is, it will help you in measuring the resistance, the conductivity, etc. Then, what is that portion of the wafer called?
A die.
Yeah.
Or
So, similar to the die, we have other things as well, right?
Flat, ma'am.
No, flat
Flat.
flat is the edge. So if you have a wafer like this, sorry, my drawing skills are a bit weak. So yeah, if you have something like this, and in that itself, it will be divided into many sections like this. So first of all, this is our primary flat. So and as we already said, if it is a primary flat and it is only primary flat, it is P111, right? This is a P11 wafer and it has many regions on top. Suppose it, and these lines are known as, can anybody tell me what these lines are called? These lines,
some street word is, I think, street.
no, scribe lines.
Exact scribe. Right.
Scribe. These lines are called scribe lines.
Scribe lines. Right.
Yeah. And again, these units, they can be divided into two types. There are two types of them. One is the test die. Test die and the actual die. So these test dies and actual die, what they do is that this particular region can be used for, it works as a standalone unit. That is, in case we are using it in as part of the IC, so what will it will like its resistance or say its conductivity etc. will be measured. So these units will be used for that testing part. So these are known as dies or test dies. Is that clear? And at these edges you will have these incomplete dies, right? Those are known as edge chips. So these are the different regions in a wafer. So is that clear?
Like, ma'am, the test die will be different from the actual die, or it is the same?
No, test die. The thing is that test die is the one that will be used for testing, and it is assumed that suppose if n number of tests comes as same, the dies will be having the same functioning.
Like it will be of the same everything,
Yeah,
like whatever process we do on
the
the
test
normal
die.
dies.
Yeah, it will work on the test die. So whatever process we test on the test die will work for the normal die as well.
Okay, fine.
Yeah.
What is the need of marking one? We can take any of them and we can try now. What to mark, like this is the test die. I can take, like every die has gone through the same process. I can assume like another part also. Why I shall fix that is the test die.
The thing is that, see, there are many of them, right? So if we take an n number of dice and test them, and then we assume that all the dice will work fine, just by testing a single them, or one thing is we cannot test all of them. It will be a very time consuming process. So even here we are talking about a single wafer, but when we are manufacturing in bulk, testing each die won't be possible. So what we do is that we will take a wafer from the lot, we'll test a few dice in them, we'll test the test dice from them, and then if that test goes beyond a particular level of quality, we assume that the entire wafer is working well. Like every wafer testing every die won't be like practically possible, right?
Like my question was like, ma'am,
Yeah,
since we have a test die,
yeah,
like after every process, we will see measure in the test die parameters and conclude that our process has
has
went
well.
well.
Yeah, yeah,
Question is, like you have marked, for example, you have taken these two as your test
yeah,
dies.
yeah,
Like after some process, you were to measure these two. After one process, you are planning to measure these two.
yeah.
Why you are planning to measure only those two? You can measure some other twos also, na?
Yeah, that is what, and it's not like only one will be there. And this is not like the size. In a single wafer, there will be a number of test dice. It's not like only one is there.
Like what is the need to mention it as a test die, since you can test any one of or any one or two of them and you can conclude? Why to mention them as a test
See,
die?
like when we are using something for a like process, we cannot use the tested one, like what we have taken and we have tested. We cannot give it to the people who want it, right? Suppose I am a supplier, means that I'll test in particular parts of it and I'll mark it as test die. And the person who is using it in their IC, they won't be using the test die, right? Because already I have maybe clipped it to my resistor, put contacts onto that, etc., etc., etc. So they can't reuse it, right?
Okay, ma'am. Thank you.
Yeah,
I understood.
yeah. Okay. So, okay. So next is in doping, there are two types, right? What are the two types of doping? Briefly in the first lecture.
Diffusion,
Yeah, please go ahead.
diffusion and ion implantation.
Yeah. Among diffusion and ion implantation, which one of them has minimum lateral spread?
Ion implantation.
Yeah. So basically, you know the difference, right? In diffusion, what we do is that from the surface, it will be heat driven and it will thermally diffused into the bulk of the material. But in ion implantation, what will we do is that a high impact ion will be impinged, right? So if you see inside a material, in case of diffusion, suppose the doping goes all the way like this. In ion implantation, what happens is that it will be more focused. Only the particular region we want will get doped. So that is why we say the lateral spread is less. Is it clear?
Yes, ma'am.
Yeah.
Yes.
Then, so the current level of device integration that is used in materials now is
12 mm wafer.
sorry.
12-inch wafer.
No, no, that is what which criteria does it come in, like VLSI, ULSI, etc., etc.
In ultra.
Yeah, so it comes in ULSI. Okay. So now, can anyone tell me the different types of layering operations now? Layering operations. What are layering operations, and what are the two types of layering operations?
Hello.
Yeah, tell me please. Sure.
Grown type, layering, and deposited type.
Yeah. So one is grown type and the other one is deposited layer. One is grown type, one is deposited layer. In grown type, we have oxidation and we have nitridation. And in deposited layer, we have CVD, sputtering, electroplating, etc. etc. So difference, do you know, in case of grown layer, what we do is that an oxide layer or nitride layer will be grown on top. But in case of deposited layer, an external material will be deposited either by sputtering or chemical vapor deposition. Chemical vapor deposition, if you know, means that our wafer will be here and whatever material you want will be at another part of the chamber and it will be first vaporized and then chemically deposited on top. But in case of oxidation and nitridation, what happens is that a material will be first deposited and then it will be oxidized. Then that is the oxidation process. And this, if it is, for example, say aluminium we are putting and then it is converted into Al2O3, then that is the oxidation process. But in case of the deposited layer, what we do is that it will be externally deposited on top of our wafer. This is the difference between grown layer and deposited layer. Is that clear? Yeah. So like these are the main things that we have discussed in week 1. So does anybody have any doubt from week 1? If you have, please do ask now. Yeah, since it is a first session, I too am keeping it short, but from next week onwards, you can expect a session that would go on for say at least 1.5 to 2 hours. So, and if you have any doubts from the previous week also, suppose you go through the notes from week 1 and then you get a doubt later on, that time also please feel free to ask. Yeah. Anybody has any doubts, anything?
Ma'am, one question actually I have written in my notes, sir.
Yeah, tell me.
In IC 1959, J. Kelvin
Okay.
from Texas Instruments, and they introduced the IC with germanium material.
Okay.
In that lecture, sir told me that there is 5 components: transistor, diode, capacitor. I wrote only 3 components.
Okay. So
And
can you do one thing? Like your actual question, can you just mail it to me so that I can compare it with the video? Like I don't remember the video right now. So can you just frame the question and mail it to me? You know my mail ID, right?
No, ma'am.
Yeah.
Actually, I posted the question in the portal. Actually.
Okay. Portal is handled by another person. So basically, 3 of us are there. One person will be handling the portal and the group discussion forum, and there will be 2 TAs. So my mail ID now I'll post in the chat box. So please send that particular question to me.
Okay.
Yeah. Is it not able to send it? Yeah, santra.pmrf@gmail.com. So this is the mail ID. Like what difference you felt between the video and the like whatever you have noted on, please frame that question and send it to me. I'll go through the video and I'll confirm. Yeah. Anybody else, any doubts or anything you want me to include in the upcoming sessions?
Ma'am, I have question from week 2. Shall we restrict that for week 2 or we can take it now?
Week 2, I think we can do it next week.
Okay, fine.
Yeah. And yeah, that is one good thing. Like whenever the videos are released, even if the live sessions are 1 week behind, please keep yourself updated with the videos of that particular week, and you just can note down these questions. Yeah. And when is your first assignment submission due date? 7th. Okay, fine. And after 7th, in case you are not getting answer, you felt any answer was like it didn't match on what you studied and what was in the video, anything like that, please do take it up with me. I can discuss that as well.
Okay.
Yeah. Anything else? Anybody? Nothing? Is that all?
Yes, ma'am.
Yeah, if that is
Yes,
the
ma'am.
case, then
Thank
we
you.
can wind up for today. So let me talk to the NPTL team whether there is a possibility. And what is your preferred time in that case? Suppose they are telling that we have an option for changing the time. What should be a preferable time? Like, should I keep it at 7:30 or push it even further? Or maybe earlier, like 5 or something like that.
5 will not be a suitable option
Okay.
from uh,
Like the
7:30 or 8, I believe it would be okay.
7:30.
7:30 or 8.
Okay, so let me talk to them. So first session will be like 6 to 7:30 and second session from say like 7:30 to 9. Like that.
Right.
Yeah, so let me talk to them. Yeah,
Thank you.
yeah. Thank you so much for joining everyone.